Very good morning, everyone. In the today's class of this operational research, we would like to learn regarding the single and multi-channel model waiting lines in the operational research subject. We have gone to the waiting line systems and the different characteristics that are involving in the waiting lines. As per the periodical basis, streamlining conditions in the case of these waiting line systems and need to process any kind of manufacturing processes within the company or industrial sectors that are being utilized. With the service oriented as per the medical characterizations or else the medical manufacturing accessories or laboratory aspects, the serving of materials from one place to the another place without any human involvement. There is a process of automatical transformation of materials from one place to another place utilizing this conveyor belt system. And based upon the reserve basis system or else FIFO activity, that is first in and first out. Next one is an the optional conditions, that is as per the priority conditions, emergency criteria, that is the manufacturing which is being done that need to be let out even before than the previously entered object to the manufacturing machinery. Coming to the strategies or different stages that are existing in the different operational waiting line systems. Moving on to that, we are having single channel system and multi channel system and the counter situations that are being existing in the case of satisfying this waiting line management. If the priority is at most in emergency category, the FIFO activity will not be supposed to follow in any of the criteria for commencing the emergency model that are being accessed, that are to be accessed randomly in the output channel. So in such cases, the FIFO activity may not be followed in the criteria. Let's go on with respect to the in detail related to this single channel system and this multi-channel system that are utilized to grow and complete the tasks that are being assigned in a rationalized manner. We are first model A, that is single channel system. Here we are having the following sequence of steps that arrivals are served on the FIFO basis, that is first in and first out basis, and every arrival waits to be served regardless of the length of the queue. And with the independent of proceedings, arrivals but the average number of arrivals does not change over the time. It's nothing but the arrivals are independent, nothing but from the different channels the input is being fed to the processing unit. But the average arrivals that will not be changing with respect to the time, because the machinery will be accepting continuously towards the input and it will be identified from which channel it has been obtained. If there are any similar kind of inputs that are being entering into the processing channel, then there will not be any normal identifications. If the almost all the input machineries are having the similar dimensional accuracies, then it is with the same material also, even it is impossible to identify in a perfect strategy that from which channel it is being getting input to the processing section. So that is the independence characteristics. And even the arrivals are described by Poisson's probability distribution and come from an infinite population. Coming to this channel, these arrivals are very well described with respect to the Poisson's probability that we have been identified or learned in the previous classes, and will be coming from an infinite number of populations, or also can be analyzed by the Poisson's probability distribution. Moreover, the service times vary with respect to one customer to the next customer, because the FIFO activity may be or must be followed in an most cases, and later on the preference ratio processes need to be commenced as per the service oriented systems. Service times occur according to the negative exponential distribution, obviously, and the service rate is faster than the arrival rate. So these are the similar axes of points that are being meant over this. And the nominal formulation that has been extended in the case of the single channel system, that average number of units waiting in the queue, there is lambda square by mu of mu minus lambda. The formulations, different formulations for average time of unit spent waiting in the queue, utilization factor for the system is known. P naught is the probability of the n number of units. Probability we are considering the 0 unit, P naught 0 units. If the n number of units are being service unit is an ideal, it will be increasing further. That is, it may be of P1, P2, P3. So obviously, it will be increasing. And later on, P of n greater than k, probability of more than k units in the system, where the n is the number of units in the system. And there is the formulation for this calculation. It is lambda by mu of k plus 1 past p. So in the single channel, as you have been specified, that lambda is having 2 cars per hour in the service session, and mu is equal to 3 cars serviced per hour. That is nothing but a shortage of 1 car that is having the capability of being serviced with respect to the manual power or automatical power. We are having three different cars, or else the similar cars, or any of the 3 cars can be serviced within an hour, but we are having only 2 cars that are arriving per hour. Here, the working environment is very much heavy when compared to the input. Output or processing schedule is very much alert, but the input to the processing is limiting. So for that, we'll be identifying the L value, W value, and LQ value. And we all know that Ls is equal to lambda by mu minus lambda. We are having 2 cars in the system on average. So averagely, we are converting this 2 cars that are getting per hour for servicing, and how much time will be the waiting hour in the system. So averagely 1 by mu minus lambda, that is 1 by 3 minus 2, that's 1 hour average waiting time in the system, and waiting in a line. So that is the time that is being waiting in a queue. That is 1.33 cars that are being waiting with respect to the formula of lambda square by mu of mu minus lambda. As we are having the lambda is equal to 2 cars that are being arrived per hour, and mu is 3 cars serviced per hour. Awaiting of this average waiting time is being found out with respect to lambda of by mu of mu minus lambda. That is 2 by 3 are equivalent to 40 minutes average time that is being taking for the waiting time period. Coming to the Poisson's ratio, that is lambda by mu, 66.6% of the time mechanic is busy. So it relates that a maximum characterization, that is 40%, among these 3 hours of time, 40 minutes need to be spent in an ideal mode by the working person, and only 66.6%, nominally equal to 67 percentage of time, is being busy on the basis of this mechanic work. Coming to an ideally waiting time period, that is P naught, that is equal to 1 minus lambda by mu. Nothing but any of the mechanic is being sitting in an ideal position, or else these persons are being existing in an sequencing mode, or else in an automatic. If the system is automatically a working system, even that system should be in an ideally working mode, or else even in the case of halting mode, that is 33 percentage is the probability that the system need to be kept in an ideal position, that is without any working scenario. And this is the sequence of agitation, that noting that equal to 1 minus p naught, that is 1 minus 0.33, and equal to 67 point or 66.66% is an average time period that is being taking place by the workers in a working mode. Moving on to the economical constraints that are being, if you have been considered for a single channel environment, calculating the investment that is being spent by the customer, or satisfactory aspects that are being done considered by the customer, or dissatisfaction when considered in the case of loss that is being taken place by the customer. Coming to the point of this customer dissatisfaction and lost goodwill is $10 per hour, and working in weight queue, that is equal to 2 by 3 hour, and average, if you have been considering that 16, if within the 24 hours per day, that is 24 hours, but total arrivals when compared with respect to 2 cars per hour, among, instead of getting 3 cars per hour among a day, that is total arrivals is equal to 16 cars per day. Hence the mechanic salary will be of 56 per day when compared to the calculation part. That is nothing but, for that particular case, how much time that the customer need to be spent his time during the working hours by the mechanic. This is equal to 2 by 3 waiting into a number of cars that is being arriving per day. 2 by 3 of 16 is equal to 10 hours into 2 by 3. So this 10 hours of the time period that are being set in a waiting period, or else waiting when the servicing is being done by the worker. Customer waiting time cost, that is $106.67 of economy, and total expected cost is equal to the sum of the waiting time cost per customer spend of this waiting, nothing but the salary of the mechanic, that is equal to 106.67 plus 56, that's equal to 162.67 when considering the dollars, or else in the rupees category when, when we have been converting the calculations, or else the currency input. Moving on to the multi-channel model, Amazon, let us consider Amazon number of channels open, and lambda is the average arrival rate. M is equal to the average service rate at each channel. Moving on with respect to the Poisson distribution of Poisson's ratio, we are having the formulation of 1 by sigma of n is equal to 0 to m minus 1 of 1 by n exclamatory of lambda by m of n plus 1 by m dash of lambda by mu for m mu by m mu minus lambda. Here the consideration that for m, there is a number of channels that are being open, and the product of average service rate at each channel is greater than the lambda, nothing but average arrival time. Considering in this case, we are having that ls is equal to lambda mu of lambda by mu into p naught n by m minus 1 of m mu minus lambda whole square plus lambda by mu. Coming to the servicing work time period formulation, that is lambda mu of lambda by mu of Poisson's ratio, or waiting, that is a null period. Null period in the sense there is no any working during that particular time period, plus m by m minus 1 of mu m minus lambda whole square is equal to 1 by mu of ls by lambda. And next, even the length of the queue is equal to ls, that is an service period of line minus lambda by mu. And by this entry of or else the length of the queue, how much time it need to be maintained when it is being in the servicing period, that is nothing but working hours. So working in a queue is equal to working of the servicing minus 1 by mu, there is a Poisson's variations, is equal to length of the queue by lambda. So here lambda specifies the n number of vehicles that are being entering into the system for getting serviced in n number of variations. So n number of variations, we have already specified that n m into mu is definitely greater than equal to lambda, greater than lambda. Not is it all the equal to, it is definitely greater than the lambda. That is nothing but average working hours with respect to the m number of inputs that are being definitely greater than the lambda. So by this we will be having the possible variations, and we'll be having looking out with respect to an example and the simplification of those values in the obtained formulations in multiple channel, considering the value of lambda is equal to 2 and mu is equal to 3 and m is equal to 2. Let's recall once again the parameters here, where m is the number of channels that are being open, lambda is the average arrival rate, mu is the average service rate at each channel. So specify these three technical terms once again. M is equal to the number of channels that are being open, and lambda is the average arrival rate, and mu is equal to average service rate at each channel. So presently we have been looked with respect to this line waiting in a queue and servicing line that is being existing, and working in a queue and servicing in a queue. So considering an example here, lambda, and hence lambda is an average arrival time is equal to 2, mu, that is average service rate at each channel, that is 3, and m, that is number of channels that are being open as an inlet to enter the processing or as the service period. So here service in the sense we are definite, we are very much clear that the cars that are being arriving to a service or mechanic sheds for getting serviced. So primarily moving on with respect to the Poisson's variation, the rate of indeed to find out the ratio within the particular time period. So P naught is equal to, we are having the formulation and substituting the values of lambda, mu and m. For that we are getting the value, it is 1 by 2, that is 0.5. And moving on to the line of servicing, we are getting the value of 3 by 4. And work or waiting time in the service oriented, when the service is being taking place, that is 3 by 8. And coming to the line of q, that is 3 by 4, that is ls minus this formulation basis of 2 by 3, that is 1 by 12. And waiting line q, the ratio that is being followed, 0.415. And coming to the basic difference identification between these two, that is single channel and two channels. Previously we have been got with respect to three axes, there is single channel, multiple channel with respect to a particular target. First one is an P naught Poisson's variations, line of servicing, length of servicing, and waiting line. So the work time that is being existing in the servicing period, and the length of the queuing process, and the time or working time or waiting time that is being existing in the queuing process for getting serviced. For a single channel, in the previous examples we have been seen that is 0.33, but if the two channels have been maintained, it will be double, it is 0.5. And in the single channel we are finding out there is 2 cars per hour, that we have service is being taking place in double channels, that is nothing but in two different variations. If you have been commencing the activity, it will be progressing in 0.75 cars, nothing but simultaneously. If the two channels have been maintained simultaneously, the work will be distributed among the two different channels. And if the two cars arrived per hour, three cars arrived per hour, instead of getting serviced within 45 minutes, that it will be completing within that 22.5 minutes itself. So hence it is being clearly specifying that the servicing time period, it is 60 minutes if the only single channel has been constituted. If two channels has been constituted, and the time will be getting decreased, that is 22.5, and length of the queue is 1.33 cars and 0.83 cars. And working time or waiting time of queue, that is 40 minutes. And hence in the two channels, if you have been considered, there will not be any highest range of working time period, that is decreased to 2.5 minutes. As per the Poisson's arrivals and the exponential service basis, when you have been considered this Poisson's ratio nominally, the channels, depending upon the sequence of channels, the values will be in a similar format, and these are the values we have been obtained in an experimental basis upon live basis of work. Moving on to the bank tellers and customers, another one more example we have been taken, bank tellers and the customers. So tellers in the sense nothing but the workers who are working within the bank on behalf of the customers. Nothing but the service that is required for the customers need to be done by this bank tellers. Lambda is equal to 18. And coming to the utilization factor, here the ratio of this service by the bank persons or executives indeed to satisfy these customers are in the ratio of lambda is equal to 18 and mu is equal to 20. Coming to the Poisson's ratio, we are all aware of that utilization factor is nothing but rho is equal to lambda by mu. And upon simplification, we are getting 18 by 20, that is equal to 0.90. And you are having the formula of waiting in a queue for getting service done by the bank tellers. That is line of queue that is being in a waiting period by lambda. So lambda is nothing but the Poisson's variation, that is until the exponential basis of work as per the preference will be done to satisfy the customers. So n number of service windows that are existing within the bank. This is first window, second windows, third windows, and four windows. If you have been considered this m is nothing but the n number of possible ways that are being existing. In the first window, we are having only the one possible window, and among that, the number of n q that are being existing is the ratio, that is 8.1, and the waiting line, that is queue waiting time in the queue, is being 0.45 hours, that is 27 minutes of waiting queue. And these are the values that will be obtained when the simplifications are done with respect to WQ, here time in a queue process, and number of queues, that is equal to lambda by mu. Right? Right. Next, if the two windows has been considered in the similar strategy, the number in the queue will be 0.2285, and the waiting line or waiting time in a queue is equal to 3 by 4th of the minute. So hence the service is being very much quick when compared with respect to this. Hence the customer need to be wait only less than a minute, 3 by 4th of the minute, and hence we can consider 45 seconds, 3/4 of the minute, the 45 second. So and hence he can approach to the bank teller for commencing of his work, nothing but for satisfying his needs by the bank, by the banker or bank teller. If simultaneously three windows has been satisfied, the queue will be 0.03 only. The number of persons will be decreasing in ratio, and even the time in the queue process will be only the 6 seconds. If the windows has been furtherly increased, and the ratio or number in the queue is equal to 0.0041, and hence the time is being limited to only 1 second of time. So there's no any waiting period, and hence this is the best service that if the n number of possible ways or has been increased for getting serviced, the customer will satisfy immediately within a less time, and his queries can be minuted or else resolved his queries by the bank tellers. That is the process of banking sector. This is one of the example that is being taken in a multiple channel base, and hence the single channel way. And furtherly, if the channel has been increased more than two, will be coming under the multiple channel way of solving the or satisfying the customers. Next, a similar way will be recalling the formulations once again. You need to calculate the constant service models. So if the simultaneously overall these exponential terms need to be organized, or else the satisfied is to be satisfied in an automatical way of solving, at that particular time we will be programming these values in the program at the shift periods, or else the particular step of the program with the formulations entry, and hence we'll be obtaining the values very much quickly. As we all aware that average length of the queue is equal to lambda square by 2 mu of mu minus lambda, average waiting time in a queue formulation, average number of customers in a queue formulation, average time in the system, there's a formulation. And if we have been considered one of the example, that is nothing but trucks. Trucks currently wait 15 minutes on average. For each and every truck, it will be waiting for 15 minutes. Truck and driver cost is $60 per hour. Automated comparator service rate is, that is mu exponential term, 12 trucks per hour can be serviced. Arrival rate is equal to 8 per hour, that is lambda. Comparator cost, that is 3 per truck, and current waiting cost per trip, that is 1 by 4th hour. And for each and every hour we are definitely, the truck driver is charging off for about 60 per hour, and hence the average current waiting time, that is 1 by 4th hour into the 60, that is he is being paid with respect to hour, that is $60, and hence it is 15 per trip. Yes, if you have been followed with respect to the waiting time calculation, as you are aware of the formulations, that average length of the queue, average waiting time in a queue, W is equal lambda by 2 mu of mu minus lambda, average number of customers in a queue, LS is equal to LQ plus lambda by mu, average time in the system, that is working service or in the service queue, average time that is being commenced is WS is equal to WQ plus 1 by mu. WQ is nothing but average time in a queue, that is also will be summated in the average system, average time in the system, until and unless the order has been confirmed and until the completion of the end work will be commencing. the time period in the case of this average time in the system. So with the given values of the truck for getting serviced in the working unit for any kind of a problems it is. For example, we just will be considering as a general service, changing of an engine oil, tightening of the nuts and bolts, and chain, etc. And next, even the wheel alignments, overall the general service. Trucks currently there is nothing but 15, and calculating of the average waiting time, there is WQ is equal to 8 by mu of mu minus lambda, this will 1 by 12 r, and waiting cost per trip. Based upon that, we will be having the one idea, that is WQ of the cost that is being spent for the driver per hour, that is 60, and we will be having the actual waiting cost, that is 5 per trip, $5 per trip. Savings with the new equipment, hence 15, that is current waiting cost per trip, that is 15, and hence there's only $5 per trip is being waiting when with respect to comparator, and hence 15 minus 5 is equal to only the 10, and this 5 will be on the savings, and overall expenditure it is 15, and savings with the new equipment will be of 10 per trip. Cost of the new equipment, that is rupees 3 per trip, and net savings average on an average cost of new amortized nothing but for an loading, that is comparator cost for loading or unloading, etc., that is 3 per truck that has been analyzed, and hence the 3 need to be discarded from the new savings equipment, that is 10 minus 3, that is equal to 7 per trip. So this is the actual calculations. And moving on with respect to a new example, that is limited population model. This is an service factor that need to be spent for calculating the n number of persons need to be get serviced with less waiting time period in the live basis. Here limited population relates to the service orientation, nothing but if any Xerox center or net center that is being existing, we need to take a printouts of 10 different papers that are existing in different formats like PDF, Excel, Word, Notepad, etc. For that, if the printer has been got damaged, we'll be going for the repair section. So like us, one net center, n number of net centers will be getting existing, and commonly we are getting the similar kind of problem that their printers need to be get serviced by this service person, repair section. So there is n number of persons may be getting arrived to this particular service person, and at that particular ratio we are considering this service factor is equal to x, that is equal to t by t plus u, where average number of running j is equal to nf of 1 minus x, average number of waiting l is equal to n of n 1 minus ef, average number of being serviced, that is upon the process, that h calculated with respect to h is equal to fnx, average waiting time. So average waiting time is equal to w is equal to t of 1 minus f by x f, that is average number of waiting time, that is l, and has its of characteristic with respect to t of 1 minus f by exf. Number of population n is equal to j plus l plus h for average number of running, that is servicing is being done presently, average number of waiting for getting serviced, the number of people that are being waiting, and next average number of being serviced h, already finished the servicing and yet to be delivered, that is coming to the h category. So we'll be having a detailed look in the tabular sessions with respect to detailed conditions, what is meant by f, what is meant by t, what is meant by u, etc. D is the probability that a unit will have to wait in a queue, where n is the number of potential customers, f is the efficiency factor, T is the average time service. H is the average number of units being serviced. U is the average time between unit service requirements. W is the average time of a unit. J is an average number of units not in a queue. And L is the average number of units waiting for queue. X is called service factor. M is the number of service channels. Let's have an finite queuing table here. That is X, M, D, F 0.1, 0.012, 0.025, 0.050, 0.060, 0.07, 0.08, 0.09, 0.100, where M is 1, 1 when compared to this D, where this EX is nothing but the service factor. M is the number of service channels. D is probability that unit will be having. F is the efficiency factor. So we are having the detailed table or the formulations here for calculating this characterization, that is average waiting time. W is equal to T of 1 minus F by XF. Average number of waiting, that is L is equal to N of 1 minus F. Service factor orientation, X is equal to T by T plus U. And the average number of being serviced, H is equal to F and X. Considering a similar one of the example in the case of this limited population, nothing but a printer problem. Each of 5 printers requires repair after 20 years. So EV is nothing but the essential of a service within a particular time period of use. One technician can service a printer in 2 hours. That is the time that is being done in a waiting strategy for getting serviced by one technician. Printer downtime cost of $120 per hour. Technician cost 25 per hour. Upon this, by utilizing the formulations, we're getting the answers related to that service factor calculation. X is equal to 0.91, very much close to the 0.90. We are having the standard relations as we have been seen in our tabular column. As per the exponential basis, we have got the standard values, and closest values can be preferred. So 0.091, and hence it is equivalent very much close to the 0.09. Hence, for m is equal to 1, d value will be of 0.350 and f will be of 0.96. And for m is equal to 2, d will be of 0.04 and f is equal to 0.98. And the average number of printers, nothing but m is, that is nothing but the j value, where m is equal to 1, j is equal to 5 of 0.96 of 1 minus f, x, that is 1 minus 0.09, that is 4.36, and m is equal to 2, j is equal to 5 of 0.998 of 1 minus 0.091, that is called 4.54. And these are the values that are preferred from the standard finite queuing table. For example, the value that we have been obtained 0.091 and is very much equivalent to the 0.91, and hence this, if it is equal to 1, that is 0.35, and 0.96 the value of f we will be considering for the calculation basis, because we need to be have the d value and f value in the formulation for getting substituted. So for any unit, if we have been taken m is equal to 2, the corresponding values of 0.044, 0.998 will be considered. So those are the values that have been substituted here. That is 0.998, 0.091, etc. And hence we will be having the values. And these are the n number of technicians, that is 1 and 2. If you have been considered 1, the average number of printers down, that is n minus j, that is 0.064. And average cost per hour downtime, that is n minus j of values per hour, that is 120, that is paid. As we will be getting the value of 76.8. Cost per hour or technician is $25, and total cost is 101.8. If the number of technicians has been increased to 2, as we have been identified from the table or column, by considering the work by single technician or else double technicians. So considering double technicians, the values will be of 4655.20, 50, 105.20. That is the total cost that is being spent here. Just for m is equal to 1 value, and for m is equal to 2 value, d value is 0.44, FL is equal to 0.998. These are the average number of printers that are being working. Upon substitution of these values, will be getting the value of this 4.36 and 4.54. And other queuing approaches, when you have considered not only for a single and a double, and additionally if you have been considered other queuing approaches, the single phase models come many queuing situations irrespective of the CAD or working situations. Variations of the four single phase systems are possible, and even the multiple phase models exist more complex situations. Nothing but one channel after completing the process one, it will be entering into the process number two, and if it is being commencing with respect to any of the process, it will be entering into the channel number two by bypassing channel number one in the cross alignment, and to the channel number three also can be progressed simultaneously. This channel number two, which is progressed, can be moved on to the channel number one if that is free for second phase of work. So these are some of the other queuing approaches, and these are the other queue of approaches we have been already seen in the previous class. So in this way, we'll be approaching with respect to the standard tabular column situations, and the standard values will be given to you in the examination point of view also. This tabular column will be given to you. Standard tabular columns will be provided for you in the examination point of view, right? And these are the single and multiple phases of the waiting lines and its resolution process of time being waiting for n number of customers to get serviced by the technicians. Thank you.